Hello, welcome to our practice problems for Chapter 8. Once again, I'm going to go through these practice problems as if you've gone through them and attempted them, and to keep the videos at a pretty good rate so you can get through it. So here we have our first problem, and we're given some information as far as this population. Now, key things to keep in mind is we're looking at individuals that will produce a change in the scores. So it doesn't really tell us what direction. Right, doesn't say that they want to increase the change or if it's going to be a decrease in change. But if we read further on, we're going to see it's in reading skills. And most of the time we don't probably want to decrease reading skills. We're always going to want to increase it. But you can make it a two-tailed test by making it not equal to. But when we're looking at some of this stuff, we got to kind of take a little bit of that common sense, critical thinking that we're going to want to increase reading skills as we go through it. So as we read the problem, we're given a bunch of information as far as our mu and our standard deviation and our x-bar. Remember to really take into consideration the values that are given. So if we're given an x-bar, that's going to be our sample. And if we're given mu up here, then we know that's going to be our population. When we have our z is equal to x-bar minus mu of 0 divided by the standard error of x, which is the standard deviation over the square root of n. When we're given this information, make sure you follow what is given to us. So if we have mu is going to be used as our null hypothesis number, and we're going to want to produce a change in score. So for this one, our null is going to be equal to 75, and we're going to want to be greater than 75 for our alternative hypothesis. You can make it two-tailed if you wanted to, make it not equal to, but for our purposes right now, when we're going to increase reading scores, the change is probably going to be an increase. When we set up our test statistic, we're given a z-test, and our values are going to be 80 minus 75 all over 15 over the square root of 25, which is going to give you a value of 3. Oh, I'm sorry. Looking the wrong part. 3 is what our standard error is. Total value is going to be 1.67 z. And this is going to be our z value. So we're going to take this and go to the back of the book. Because remember, z, oops, I don't want that. Z is just telling us how many standard deviations this value is. When we go and find 1.67, we'll find that is 0.9525. But remember, since we're going greater than this and everything in the book tells us from that value to the left, we're going to subtract it from 1. So 1 minus 0.9525, and this is going to give us our p-value of 0.0475. So our test statistic that we did is 1.67. We don't have to write z, but I'm kind of just copying over. P-value is the probability, so 0.0475. When we look at our p-value and compare it to our alpha, remember, if the p is low, the null must go. If our p-value is less than alpha, we're going to reject the null hypothesis. Our p-value is in fact less than alpha given to us here, so we're going to reject the null. When we want to restate the decision, we would state that there's sufficient evidence to warrant the rejection of the claim that mu equals 75. I'm not going to write all that out, as you can read it on the PDF file of this. Moving to number 2, same thing here. We're looking at SAT scores from Sacramento High and then Sacramento County. Truly, we're trying to find if there's a difference, right? But we're not given if we want this difference to be greater than or less than. We're just looking to see if there is a difference. So when we set this up, our mu is going to equal 1020, and since we don't know what direction we're going in, we're just seeing if there is a difference. We're going to say it's not equal to, because we don't know if the test is going to be higher or lower compared to the population average here. And so we say that it's not equal to 1020. We set up our test statistic. So when we go through all this, it's going to be 1100 minus 1020 all over the standard error of x, which is 144 divided by the square root of 144, which is going to give us a value of 6.66. So our test statistic is going to be 6.66. We know if we go look this up in table B, right, because this is going to be equal to z. If it looks up in table B, we're not going to find 6.66 because our table doesn't get that high. So if we go to 3.5 and up, it's going to be 0.9999. If we look, that's going to be 0.9999. That's at 3.5, so of course we're going more, and this is going to be less. So if we wanted to look at like a one-tail test, it'd be like one tail. We would say, it's equal to 0.0001, or you could say it's less than 0.001. Since it's a two-tail test, we would divide that value by 2, so we'd say, it's even less than 0.0002 for two-tailed test, because we're dividing our p-value by 2. Once again, our 0.999 is what that cumulative probability from that value to the left, and since we're doing not equal to, we're going to take 1 minus that, and then divide by 2 for two-tailed. Since our alpha level is 0.05 compared to our p-value is less than alpha. If the low is null, the null must go. We're going to reject the null hypothesis. Our p-value is less than our alpha. And then you want to restate the decision, you could say that there's sufficient evidence to warrant rejection of the claim that mu is equal to 1020. Once again, I'm going to not write all that out because that just wastes a lot of time. Number 3 is our sample size. Number 3 is you're given a sample size and you're actually figuring out the power of a test. Now, I'm just going to kind of go through this and set it up for you, but we're not going to go too much more into it. 1 minus beta equals power, which is designated as our Greek symbol, and our equation for that is a negative z of what I like to do, 1 minus alpha over 2, so our z percentile, the negative value, plus the absolute value of our mu 0 minus mu of a times the square root of n all over the standard deviation. So we know if we're looking at all the values here, n is equal to 40, mu is equal to 75 milliseconds, standard deviation of 12. Well, we're trying to increase the score of 4 milliseconds, so that's going to be the 75 plus 4, which is going to give us our 79. So we rate all this out, and we're doing the hypothesis test at 0.05 alpha. So when we rate this all out, negative 1.96, which would be our z of 1 minus alpha of 2, 95% confidence, added to the absolute value of our mu of 0, which is 75 milliseconds, plus our alternative, which is 79 because we're adding 4 to it, divided by the square root of 40, which is n, all divided by the standard deviation of 12. And work all this out, you're going to get a value of 1.1481. And then when we go and look this up in the value book, we find that our power is not very strong. We normally want our power to be 80% or higher for any kind of test. Once again, this is kind of just going over these values, but we're not going to get crazy into determining power. Just know that power and beta go together, just like alpha and confidence go together. Power and beta will sum to 1, and confidence and alpha will always sum to 1 as well. So if you know alpha, you also know the confidence, and if you're given power, then you're also know the beta. So number 4 here, researchers pre-established rate of false rejection. Another name of false rejection will be our alpha level. So do you set an alpha level prior to conducting a test for significance? The answer is true, you do, and you don't change it. Number 5 here, let's see if we can get through some of these multiple choice real quick. So which of the following test statistic, which of the following test is not necessary prior to performing a power calculation? So we kind of just did power calculation, and we go through, you don't need a false positive rate of the test, but all the other values are needed. Number 6, which is not necessary for sample size. So once again, going back in the book, looking at sample size, you're going to need everything but C. C is not needed. Just think, to look out for is not necessary, not necessary. So all the answers here, A through B through D on number 5 are all needed. A, B, and D are needed for number 6. Which one is not necessary? Just paying close attention to the words that are used for the problem. Number 7. If we have a p-value, which the best describes the correct interpretation resulting from the statistical test, and when we look at this, the probability of event occurring given the null hypothesis true. The null hypothesis has to be assumed true always, and that's when we're getting a p-value. Remember, the p-value is just the probability that this event occurred given the null hypothesis true, and that probability is in turn what the probability of developing a type 1 error is. That's what we're doing. So the very small p-value is there's less likely an error developing a type 1 error, which is rejecting the null hypothesis even though the null hypothesis is correct. 8 here, so which of the following statements most adequately summarizes the conclusion statement resulting from a p-value of 0.03. Once again, a great way to do this is just always remember that if your p is less than your alpha, right? If your p is less than alpha, then you're going to reject the null hypothesis. So this is just one of those where if you just set this up, your p-value is always going to be 0.03. And then if you look at A, alpha level 0.05. Well, this statement is true, so you should reject, right? That would be correct. But A says we fail to reject. So it can't be A. And if you go through and do each one of those for each problem, you'll see that the answer D is the correct one, where if we reject the null hypothesis alpha level 0.01, so alpha level 0.01, sorry, not 0.01, it's 0.1. And our p is less than alpha, so we our p is less than alpha, so we reject the null hypothesis, which is what's stated here. We reject the null hypothesis alpha level 0.01. Number 9, which of the following p-values can be considered statistically highly significant? The book doesn't really cover what is statistically highly significant, but if you can kind of put together what is going to be statistically significant, well, anything less than alpha level 0.05 is going to be like significant because that's what we're looking at, and anything less is going to be even higher, right? Because the smaller p-value, the more evidence you have to reject a null hypothesis, and statistically highly significant would be a very low p-value, so 0.001 or anything 0.01 and less would be there. Number 10 is which of the following best describes the alpha level in statistical testing. Just going through this, you can kind of probably figure out the probability of type 1 error. That's what the alpha level is really giving us here. Remember, when we're alpha level, what is the probability, or how much percent are we willing to give due to chance of something happening, developing a type 1 error. Now 11 and 12 here, the key things are what best represents a type 1 error. So we already know a type 1 error is going to be we reject the null hypothesis even though the null hypothesis is true. So if we kind of look, we already know A and C are out because that's failing to reject. And what best represents a type 1 error is we're going to reject a null hypothesis. So then when we look at these values, so B is reject the null hypothesis that the weight loss program showed no benefit after a test results in a p-value of 0.15 and alpha 0.10. When we look at that, we see that a p-value of 0.15 and alpha 0.10 we should fail to reject, but if we actually did reject based on that, that would be what's considered a type 1 error, right? Because our p-value is not less than alpha, so we should have failed to reject, but since we did reject, that's what best represents a type 1 error. Same thing for number 12 when you look at it. We're looking at what best represents a type 2 error, which is when we fail to reject a null hypothesis, even though we shouldn't have. So once again, we're going to be able to take out B and D, but when we look at it, if you look at number C, we failed to reject the null hypothesis in the weight loss program that had a p-value of 0.03 and alpha level of 0.1. So our p-value is less than alpha, so we should have rejected, but in fact, the type 2 error that best represents is that when we have a p-value less than alpha, but we should have rejected just based on the data we collected. All right, we're going to move to number 13 right here and then call it a day. So here we're looking at a new diet program, and what we really want to do is just find what our alternative hypothesis should be. So it's giving a null hypothesis of mu equals 10, and when we have a null hypothesis of them equals 10, and we want more than 10 pounds in a 2-week period, so our alternative hypothesis should be mu is going to be greater than 10, right? So remember, our null and our alternative hypothesis have to have the same value number, so it can't be 6 in there like that at all, so C and D are completely out. And then when we look, mu is going to be less than 10, no, because we want to gain more than 10 pounds in the week, so it's going to be B, because mu is going to be greater than 10 pounds, and cross out E. And that is how we look at that when we're looking at the difference between null and alternative hypothesis. All right, that's going to conclude for this video. I'll see you all in the next one.